Hello and welcome. Here we are in lecture two. As you remember from before, we're going to do half of lecture two and then take a quick break and then do lecture three because we have these 90-minute sessions. Um, to make sure the recording is going. Yes, it is. So we are good to go. So remember last time we were actually trying to close the loop, right? We wanted to show just a little bit of Chisel and then see hardware design. And so we only did half that loop last time. We did a little bit of Scala, and today we're going to do the rest, a little bit of Chisel, and then we'll actually go into more detail in the following lecture about actually writing some combinational logic. So this is from last time. I do want to draw attention to the fact that these slides are not just Jupyter notebooks, but they're open source, and you can and should run them, right? So if setting up this stuff's a little tricky, which it is, you can just run in the cloud with Binder. And so actually right now I'm running myself from the cloud. So I'm not even using my laptop for running Jupyter right now. So that's cool. Very helpful thing. So we covered this last time. We introduced Scala. We got going. We showed, literals in Scala. We showed types, type inference. We emphasized we prefer to do val, that is immutable, whenever possible. And then finally we got to this point where we paused, right? Where, okay, we've learned a little bit about Scala. Show me the Chisel. So how does Chisel work? Well, Chisel is this language we're using, which is really just embedded in Scala. So technically when you're writing a hard design in Chisel, you're just writing a valid Scala program. It just so happens that Chisel is a library inside of Scala that provides functionality we need. And because of some nice features in the Scala language, Chisel at times feels like its own language, and thus we can go ahead and write things as we need to. And so there's a lot of times Chisel feels like its own proper language. There's a handful of times where you'll see it even today. There's some stuff there, and the reason why that's there is a boilerplate. You kind of need to make it work as a valid Scala program. But in general, there's some nice stuff there. So let's see what we're talking about. Um, to give a big sense of what I'm talking about, so when you write your designs in Chisel, right, you're going to make a file that's a valid Scala program. It's a .scala file. With the tool flow we have set up, it's going to go through the Scala compiler, and it creates a program, right? It's a legitimate Scala program, runs on the Java Virtual Machine, the JVM. And then, Chisel is a library it's able to use to do what it needs to do. And then when the program runs, it produces the circuit. And so the circuit, technically it's in a format called fertile or .fir, but more importantly, it goes from a program to a circuit, right? As some sort of realization of the hardware you want to have. Um, what you do with that circuit will show another slide later today, what we call the backend, to see what you can do with that. But for now, it's just, okay, I have this program. My program's a hardware generator, and it produces a circuit. So I give arguments to my program, and it spits out a circuit. That's kind of what we're trying to build. Cool. So let's go ahead and fire up some code. So this is, once again, some boilerplate code. It's just loading up the Chisel environment here in Jupyter. It's going to be a little slower today because I'm using the cloud instance, but it's doing it. So here it goes. Might take about 20 seconds. We'll see. Actually, no, I'm going to go to the next slide. We'll come back and make sure it's done in time. So uh, let's say you're writing some Chisel, right? What can you do? Well, you remember just, on Tuesday, I showed you some Scala types. Here are some Chisel types, which technically are in Scala, but we'll say where Chisel distinguished them. And the reason why we're so obsessed with types is it's actually one of the things Scala does, where it uses lots and lots of types and is constantly checking types with the goal of catching errors at compile time, right? We don't want to have our code compile and run and have this subtle, hard to detect bug later on. We'd rather be told right away, right? So these compile time bugs, remember, are really just almost typing time bugs. If you're using an editor that has code completion and syntax checking, something like IntelliJ, it'll tell you right away, hey, this does not make sense. And a lot of things they tell you about is these types don't line up. And so for that reason, like I said, there's types in Scala and there's types in Chisel, and they look really similar. And so there's some kind of ways to cast back and forth between the two of them, right? So for example, zero by itself, we saw that last time. That is just a zero and an integer in Scala. But if we want to turn it into a bool, which is a Chisel type, we can actually use this .b syntax. It's actually, like I said, everything's an object in Scala. So even the number zero as a literal is an object. And calling .b is able to convert that to a bool, which is a single bit, Boolean signal in Chisel. Now, notice how bool, which, pretty clear, binary signal, great. Uh, that's different than Scala, which has a Boolean type, right? So you can see that right here, where we have, a zero, we're casting to a bool. We have true, which is a Boolean, and then we cast this one also to a bool, right? So go ahead and run this code snippet and we'll kind of see this come together. Hopefully the prior slide is done, which it is. Great. So what do we see? Well, like I said, the first line, yeah, we had 0, we cast that to a bool. Great. Second thing, true and false in Scala or Boolean, that's a Scala type. We use .b to cast it, sure. And then, we declared a chisel bool with a value, sure. Let's say, for example, I forgot to put that .b on there. Let's see what happens, right? It's going to tell us right away these types don't line up, right? I said the thing I'm making is a bool, and it's a Boolean on the right side, right? That's going to be a mismatch. Um, Sorry, I got to get a microphone in place. Great. So these are things to keep an eye out for. Now, I should point out that this decoration is not required, right? We could, of course, do that. That should also be fine, right? It'll infer to type correctly because it knows it's on the right side of the equation. Um, Going on to multi-bit signals, there's something called a uint, or signed, of course, unsigned integer. Um, what's interesting about this is kind of like a bus in Verilog. Um, you can use .u to create it. The width itself can either be explicitly set or actually left unset, and the tools will infer it. And so you can see all these kind of situations here. So in this case, we're declaring a 6. That's a Scala integer. We cast it to a uint with the highlighted text above. Then we get a uint. It's going to infer the width of 3 bits. And it does that based on, okay, how many bits do I need to hold that number? That is the minimum number of bits I need. The Chisel width inference engine is actually pretty clever. It'll go through things and try and figure things out. If you specify too few widths, it will tell you, you know what, I can't quite figure this out. You need to give me some more widths along the way. But in general, it's pretty handy. And sometimes, as a hardware designer, you know exactly what width you want. Sure, you can do that. So you can see, for example, given the width at the time we are doing this, we can make it 8 bits, no problem. Of course, you can make vals. Sure, same thing still applies. And then if for some reason you want to have a signed number, that's also totally fair game. That's a essent, which I'm a little bit confused why that's not visible. There it is. Somehow we got zoomed in. Uh, Great. There's the essent. Cool. Questions so far? Yes. Oh, great questions. So repeat this for the recording. When you use colons versus dots for types. So when you're labeling like a variable like this, that's a colon. So when you have like a variable declaration, or when you have that list, the argument list for like a function or something, that's the colon. The dot here is actually not so much a labeling the type. It's actually calling a function, and this function is the conversion function. And so you could imagine a much more verbose function like dot to bool. So a lot of times within Scala, we saw that earlier in this lecture. Actually, go back a few slides from Tuesday. They have like these two casting functions, right? The person that did this for Chisel decided to make this very concise, and they chose to have a less verbose name. So yeah, so dot b is actually calling a function that's doing the conversion for you. Great question. Yes. Oh, so it's cast. The question is, for recording, what's it casting it from? Whatever type the Scala system had. So literals in Scala have types, right? So a true is a Boolean, so that's going to be from a Scala Boolean to a Chisel bool in this case, right? You can kind of see that these two lines here. Um, yes, whatever type it is going to be converted from there. This comes up when you design only sometimes. Like you imagine within the hardware design, most of the time you're creating signals, collecting signals, etc. But periodically you're going to need to have a literal, right? Some sort of constant. And so that's where this casting comes in. Good questions. Saw one more over here maybe, or sure. Great. Okay. Yeah, so this is the fun part of this course, right? We can just kind of sling some code, and because it's running, you can just ask what ifs and do it right here in lecture. And for those of you running on your laptop, you also can just play around with the same code. Um, Cool. So, okay, we have some chisel types. What can I do with them? Well, most things expect to exist, right? You can do logic operations, arithmetic operations, bit ops operations, comparisons that are relational, shifts, etc. All those things exist. But I want to kind of point out a few caveats along the way. Um, the one that's a little bit surprising to some folks is actually the equality test is three equal signs. So why is that the case? Because two equal signs actually is an important part of the Scala language itself. And by overriding that functionality, you'd get some surprising behaviors in certain places. And so as a result, they chose to use three equal signs for equal, and for not equal is this interesting thing, which pictorially does kind of look like, a slash three equal sign. It is not equal. But so those are the only operators which have characters that are different than you expect. The rest of the ones are the ones you expect, right? You have add, subtract, multiply, divide, remainder with mod, bitwise operations, not, or, and XOR. Um, those all are kind of along the way you expect. Some other things we'll see later at the end of the next lecture, things like, if you want to extract certain bit ranges, fill a bit range, concatenate, muxes, reductions, yeah, those all exist. But that's there. Now you may be saying, wait, how can I remember all this? Um, this link takes you to the Chisel cheat sheet, which is a nice page which you can print out a double-sided paper and just has this kind of handy reference, right? So you can say, oh yeah, I want to do a logical, and oh yeah, that's the way to do it, right? And one of the things interesting about that is not only does it tell you the syntax in case you forget, a variety of Chisel features, it also has some helpful hints. You'll see, for example, with things like with inference, you perform an operation, you're curious, well, how big is the result going to be? This table will kind of remind you how to compute that if you're curious. Now, when in doubt, of course, you always set widths explicitly, but sometimes it's nice to kind of let the tools do things. So yeah, here we have, A and B just fine. Um, Now you might expect me to do this line right here, but you can see if my comment, it's not going to work. The reason why is, although, like I said, Chisel tries its best to give the illusion of being a language, in this very exposed state of being inside Allman, inside Jupyter, and outside of a class context, there's just not quite enough for Chisel to get going. And so uh, you'll see this is not really a limitation in practice. Usually everything you declare is what's called inside of a module, but if you're playing this round right now for the first time, you may get that error, and that's what's going on. Cool. Questions? Okay, let's actually make a module. So, how about a really simple module? We'll just build an XOR gate, right? So we're gonna call this my XOR. And what do? Well, you can treat a lot of this as boilerplate, but kind of the key thing is, sure, you name it. You have IOs, so we have some inputs, A and B, which are each bools. So that's gonna be, a 1-bit signal. We have an output C, which is, also a bool. And you can kind of see how we're setting this up, inputs and outputs and giving them types. And then for the actual functionality, what do? Well, this is the XOR operation. You may recognize this caret symbol for doing XOR. So yeah, we're XORing A with XOR B, sure. And then we're connecting it to the output C. And so yes, that's the Chisel code on the left. On the right, you can see a diagram I drew showing the functionality, right? There's a single XOR gate inside this my XOR module, and we have these IO, these ports, right? And you have the two inputs coming in, connected to the gate, and then of course they come out as output C. So we'll be doing modules all quarters. This is kind of the very first, hello world of modules. Questions so far? Cool. Okay. So then, now that we've declared this module, so what, right? Like, have I made hardware? Well, no, I've made a hardware design, right? And technically, what I've done is I made this class that when it runs, it makes this XOR module. And then what am I going to do with that? Well, we can do a few things. For today, what we can do is tell it, hey, you know what? Turn that circuit into Verilog. So we can do that. It's taking a little bit of time because the cloud's a little slower than my laptop, but it should come out. There it is. So you see, yes, it produced Verilog for this design. And you'll see throughout these lectures, I often will use Verilog as a way to kind of show what the hardware turns into. It doesn't necessarily mean that, we only care about Verilog. It doesn't necessarily mean that you need to know Verilog to do well in this course. It's just showing how this concretely turns into a circuit. So in this case, it's virtually one-to-one, right? You can see, if I go back a slide, um, here we have A, B, C as inputs, A and B as inputs, C is an output, and then the one-line connection. Look at the actual Verilog, it's pretty similar, right? Okay, here's inputs A, input B, output C, and then yeah, it assigns this. Um, Technically, it also has these additional ports for clock and reset. You can imagine that since they're used inside this module, they're superfluous. And the answer is yes, they're superfluous. Um, there's not really any penalty to doing this. The CAD tools, when they actually process this Verilog, will recognize they're not used and just print them out quietly, and there's no hardware cost for that. Yes. Sorry, say that again. Yeah, great question. So yeah, so the question is, why are we reset there? What happens if you're writing Chisel? So yes, the questioner correctly inferred that in Chisel, when you write a module, we don't actually usually specify the clock or reset as IO is because they're already included. So clock and reset are spread throughout the design. They are, global. They are implicit. We can see in the Verilog, of course, they're actually materialized. That's just one way that Chisel's trying to make things simpler, right? Is realizing, you know what? Um, Everybody runs on the same clock, so let's just spread that for you automatically. Now, advanced designers will know there are certain times when you want to have multiple clocks, or you may want to do something funny with the clock. You can do that in Chisel. There are ways to set the clock that goes to a module. There are ways to have multiple clocks. We don't do that in this course, but there's functionality for that because that's absolutely essential for industrial designs. The other wrinkle is this reset, where for most components, vanilla reset works great, and thus spreading it around globally and implicitly is a really nice thing to do. But you can once again imagine certain components maybe want to be a little bit more nuanced with reset, especially when you have, power on, right? If you're first powering on your chip, coming out of power on, getting a reset right, it's a really known tricky problem. Once again, for this course, you don't need to worry about that. We're just saying, hey, reset is fine. But if you're curious for, advanced real designs, yes, Chisel has support for what's called a synchronous reset, which is very common in real hardware designs to handle that power on issue. Yes. Yes, exactly. So from the answer to the question, yes, does reset assume, on pause edge clock? Yes, exactly. Yes, so these resets are all synchronous, all pause edge. Yeah, so how could you do not pause edge? This is the question. Keep repeating it for recording. A couple ways you could do that. One, if you let's say you want to do negative edge, you could expose the clock, so Chisel make the clock no longer implicit, and then negate it, so then it's neg edge. That'll be the most common way if you want to do something that's like neg edge. Uh, Alternatively, let's say you want to have something more exotic, maybe involving your resets. You may also want to then, in that case, use a synchronous reset. Um, in the spirit of types, Chisel does have a few types that we don't cover in this course, but are relevant for that more advanced usage scenario. So there's actually a literal clock type. So that way, the signal of the clock is known as passed around. With a clock type, there's certain constraints on what you can do, which makes sense. There's also an analog type, which is also useful for times because there's sometimes you want to make sure your tools don't mess with certain signals. And if all that is insufficient, there's another escape hatch in Chisel, which is something called a black box. So you're going to say, you know what? I really know what I want to write. I want to write it in Verilog. Let me write it. And you can write that, and then you can connect to it with Chisel. So it's very much like how in languages C++, you can write what's called inline assembly. You can write a little assembly and, have C around it. You can do the same thing in Chisel. You can say, you know what? I really, really want something that Chisel seems to have a very good way of expressing it, but I know how to do it in Verilog. You can definitely do that. For this course, you won't need to do that, but that functionality exists. Great questions. I love these. This is good. Cool. So, we started off with just one XOR gate, and here we go. What else can we do with this hardware design? We can also visualize it. So there's this little tool someone put together a couple years ago that exports the design to graph divs, and yeah, you can see it visually. So here you can see, for example, oh yeah, this XOR component, which is connected to A and B and outputs to C. That's kind of a cute little thing to do. For much of this course, you're going to see us typically either looking at the Verilog or diagrams I drew as a human. But this will kind of give you a sense of what's going on. Cool. Okay, so we have this, one gate module. Now the question, of course, is what can we do with it? So we said the front end takes Chisel, which is actually a Scala program, and then the Scala program generates this circuit. Now, given this circuit, what can we do? Well, with the back end, it depends what you're trying to do. Most of the time, especially like in this course, you're going to simulate that back end. That design. You're going to go ahead and attach it to a simulator and run something. And so, of course, when you have a circuit and you want to simulate, you can't just say, "Oh, go simulate." You need to actually give it stimulus, right? It's some sort of test bench, right? What are you doing to your circuit to make it do things, right? Are you giving certain inputs? Are you waiting for certain outputs? So that's something called chisel test. We'll see an example of that in just a slide. And as a result of your simulation, You, of course, can get text outputs from printing things or a waveform, a .vcd. Um, in terms of what else can you do with it, well, of course, you can generate Verilog and then pass that Verilog off to dimensional CAD tools, whether it be an FPGA flow, a ASIC flow, etc. Um, so there's a step in between these two things by a tool called Fertile. That takes in these circuit files, which are actually in this Fertile format .fir, and it does the conversion to Verilog. Um, so that's kind of thing for this course. It's kind of below the details you need to worry about, but just be aware that's there. For the most part, we'll be doing only kind of front end ish design and just taking circuits and simulating them, and if they get the correct logical behavior, we'll consider that good enough for this course. You can imagine in the real application, you'll be very concerned about the physical costs, in which case you may want to optimize and actually pass it through a CAD flow. Cool. Okay, so then what about chisel tests? This way we're going to do these test benches. It's actually pretty fun. You can write a Scala program through the full power of a general purpose language, and you can set inputs and look at outputs, right? And you kind of see how this sets up, right? Basically, okay, somehow I want to both exercise the design, right? Make it do things by setting the inputs. When we set the value of an input, we call that poking. And then we look at what comes back out of the design. That's peeking to read the value of a wire. And very often, you don't just want to read the value, you actually also want to see the value that came out matches what it should be. And so that's called an expect, where basically it's like a peek with an assertion combined. Um, so it's a really simple example, with a two input, one output Boolean gate. We only have four input cases. We can kind of just brute force all of them. So sure, we can go ahead and write this test bench. For now, you can kind of consider this to be a lot of boilerplate, but basically, yeah, hey, if I want to test 0 XOR 0, right, I poke the inputs for A and B to be 0. I then check the output, right? And we know that 0 XOR 0 should be 0. And so after running this, we just get this, object result. The reason why is it passed. Everything's good. So if we want to see it break, I can go ahead and change this. And then we see it's going to fail, right? Because it didn't match, right? It expected 1, but it got 0. And that's an example of it failing. And so, yeah, so we'll see with Chisel tests, we can kind of, nicely write a lot of these test benches and such, and often running, and it's all within the Scala environment, right? For example, if you're writing this in Verilog these days, you can write a test bench in plain Verilog, which we all know how to do. There are things you can do in Verilog test benches that aren't synthesizable hardware, but it's still not quite as friendly as a regular program. Then, of course, there's system Verilog, which has even nicer functionality to write test benches, but it's still not quite a full programming language. Then you have Scala, which is a full programming language, right? So you can imagine very sophisticated testers, right? You could have a tester that, let's say, calls into a large software library to know what the right answer for a certain problem is. You can compare, make sure your hardware matches that. Let's say Blink cryptography function. You call into the actual cryptography library in software and make sure, oh yeah, my SHA hash matches the software SHA hash, right? You can also do things like talk to database, read JSON, whatever you want to do. You have the full power of the entire Java ecosystem at your disposal, which is really, really helpful. Cool. So then kind of wrapping up about this initial Chisel foray. So for this course, we're using Chisel 361. If you don't need to memorize the number, all the code to give you is going to automatically pull in the right version. But the reason why I'm spending a minute to talk about versions is when you look at documentation online, you may, if you just search on the web, you may see, a reference to a function, a feature that's not in Shield 361. So 361 is not the newest feature out, not the newest version out there, and that's why I'm kind of warning you. So why are we not using the newest version out there? Every year I kind of check the tires and kind of see where we're at and see what can we port, what can we not port. The biggest issues with the next version is most of the benefits it provides aren't going to be appreciated in this course for the scale designs we're building. A lot of them are designed to make Chisel scale to much larger designs, and that's something we don't have a problem with in this course. But there's a lot of consequences it has. Some of those consequences, those costs and the negatives it has, is we're going to lose things like Chisel tests. So we really love Chisel test and makes it really easy for us to write our own test cases. But the newer version does not support Chisel test. They are in the process of bringing it back, but it's still not quite there. So when Chisel test is returned, this course is going to move to the newest version of Chisel. But until then, the normal benefits of the new versions don't really help us as much, and losing Chisel test is too big of a loss. What versions are there out there? right? So Chisel 361 was last made in June, a year ago, but the much more modern series is much higher C in version numbers. They've been going to this model of big number increments every year. There was no version 4. They deliberately skipped the number. The most recent version on the like head is 6.7. 7 is available as a release candidate under public development. But for this course, like I said, we use 361. It's all the labs, lectures, homeworks. From the course homepage, we link to documentation. We link to the documentation for that version of Chisel. And much of the user-facing Chisel code is the same from Chisel 361 to Chisel 6 and 7. 6 and 7 do have some user-facing new features, but the biggest reason why they made these changes is a lot of things in the back end. Like I said, those back end changes are going to make our life a lot harder for this course, but not give us the same benefits we aren't doing billion transistor designs. Okay. Other questions? Good. I'm going to go ahead and stop the